All right, we are going to continue our presentation of some basic concepts and theorems from this section on stochastic dynamic programming. That way we are tooled up in a way that we can adequately address the stochastic optimal growth model next week. So basically what we tried to accomplish in the last class was essentially introduce some notation so that we can correctly even discuss how to incorporate uncertainty into these models, right? And the main thing we talked about was the random variable, right? The random variable is going to enter into the dynamic programming problem via a first order Markov chain, okay? And we talked about how the introduction of that stochastic component alters the meaning or the interpretation of some of the basic parts of the problem. And then I tried to illustrate what all of those things mean by basically just setting up the standard stochastic optimal growth model, right? To try to provide some kind of flesh to these ideas. And I think this is where we basically left off. So the stochastic optimal growth model can be set up in the following form. The planner is going to maximize the conditional expected value of lifetime utility, where the expectation operator is conditional on the observed value of the technology shock in the initial period. That is known at the beginning of time. What the planner doesn't know, of course, is what the future realizations of the technology shock are going to be, but she does know the probability distribution from which they are drawn, right? So she can form correct, rational expectations about the future. Utility is a function of consumption, which is output, f of kt, where z affects the production function, it's a technology shock, plus non-depreciated capital, 1 minus delta times kt, minus kt plus 1, subject to the constraint correspondence, right? So we've substituted out consumption from the problem. And kt plus 1 must reside on this closed and bounded interval, bounded below by 0 and bounded above by f of kt, zt plus 1 minus delta kt. Now, in the context of introducing this model, we also introduced some new notation of these tilde variables with squared brackets and z to the power of t in them, right? That the z superscript t is a vector that denotes the whole history of the shocks from period 1 up through period t, right? And we write the notation this way to recognize what reality, that consumption at time t depends on the full history of shocks dating all the way back to period 1, right? And therefore the capital stock at date t plus 1 is going to depend on the full history of shocks up through date t. Kt plus 1 does not depend on the realization of a shock at date t plus 1. It's determined by essentially by your investment and savings decision, that is your consumption decision in period t. What is the planner doing in this problem, right? This is, again, we talked about this at kind of at the end of class last time. In a stochastic environment, the planner has to anticipate all the possible paths that the random variable can take in the future. We illustrated that in the last class with a simple little decision tree, right? Where we had 2 values of the shock and we only looked at it for 3 consecutive periods, good shock, bad shock. And we realized that with just that few number of states, there's 8 possible paths over 3 periods, right? So when we have capital N states and an infinite number of periods, we have a countable infinite number of possible paths or histories of the shocks over time. The planner, it seems insane, but the planner has to think about at time 0 what all of those possible trajectories are and make plans for optimal consumption and capital contingent on each one. and then maximize the expected utility over all of the possible paths, where that expectation can be evaluated because she knows what the probability distribution of Z is. So one way to visualize this is that really what the planner is doing is thinking about, these countably infinite number of deterministic models where Z takes on a particular history. Imagine Z is equal to 1 every period. That's one path, right? Well, what does that model correspond to? That's the deterministic optimal growth model, where the realization of Z is just 1 in every single period. And we know what the solution to that model looks like. The planner has to solve for the optimal solutions of the K's and C's for each one of these possible contingencies. That's why we call these state contingent plans for capital and consumption. That's what she's maximizing over. Okay, now that problem is obviously extremely cumbersome. Okay, fortunately, we can express the problem in recursive form by exploiting the Bellman equation. Now, ZT we know follows a random walk, right? I'm sorry, not a random walk, a Markov chain, which means that the current value of Z contains information about the resources that are available for consumption this period and capital next period, because the current value of Z only depends on last period's value of Z, which depends on the period before. Okay, so the Markov chain and these state contingent plans basically encode, if you think about it, all of the information that you need to determine optimal consumption and capital in the current period. This suggests then that we might be able to define the optimal value of capital at date t plus 1 as some time invariant function of the capital stock today, as well as the current realization of the technology shock. Because the capital stock today depends on the realization of the technology shock in the last period, which depends on ZT minus 2 all the way back to the original period, the initial period, that is. Okay, and so this suggests then that we should be able to write this or express this problem in recursive form, and we should know what that is going to look like, right? There's going to be some value function defined over the state of the economy, which depends not only on the capital stock, but the realization of the shock at the beginning of the period. And that should be equal to the maximum of the current return, U of f of kz plus 1 minus delta k minus k prime, plus the discounted continuation return, expected continuation return, I should say. Expected value of v of k prime z prime conditional on z, where the maximization is over choosing this policy function for k prime from a constraint correspondence G that depends on the current capital stock and the current realization of the shock. Now, again, let's make sure we all understand what we're looking at here. What is the control variable in this recursive problem? It is k prime, that is next period's capital stock. What is the state variable? It's the current capital stock augmented by the current realization of the productivity shock, Z. So really this is kind of an augmented state, K and Z. Z prime over here is next period's productivity shock. And from the current period, we don't know exactly what that is going to be. So we have to form an expectation of tomorrow's value function, conditional on what we know about the technology shock today. So let me point this out. One big difference between the recursive formulation and the sequence problem is that the expectations operator in the Bellman equation is the conditional expectation of something that will occur in the next period, given what the planner knows today, Whereas the expectation in the sequence problem is the conditional expectation given what the planner knows at the beginning of time, at date 0. And that expectation has to form over all possible future realizations of Z. This is an infinite horizon problem. This is a 2-period problem where you're choosing the policy function rather than an infinite sequence of state contingent plans. And of course, G is the constraint correspondence, right? Where we recognize that the constraint correspondence is the closed and bounded interval between 0 and f of kz plus 1 minus delta times k. So the set of feasible values for k prime depends not just on k, but it also depends on the state of technology Z. Does everybody kind of understand how that's going to look? We'll come back to this model specifically in the next section of the course when we characterize its solution and we look at some of the properties of the solution. But the way you go from the sequence problem to the functional equation is very similar to what we talked about earlier in the semester in the model without any uncertainty. You just have to account for these conditional expectations now and for an augmented state that includes the shock. Now, let's assume for a moment that there exists a feasible plan up here, or a feasible sequence of state contingent plans, if I want to be specific about this, that achieves the maximum of the sequence problem as well as the Bellman equation. And we'll assume that it's a unique policy solution. Then we know that it can be expressed as this time invariant policy function, pi of kz. That implies then that the Bellman equation can be expressed as the following. V of kz is equal to u f of kz plus 1 minus delta k minus k prime, which is the same as pi of kz, plus beta times the expected value of v of k prime, which is pi of kz, comma z prime, which is a random variable that we don't know the value of, conditional on information in the current period, z. So the optimal policy function pi has to satisfy this Bellman equation. Okay, you guys have any questions then about that? So do you understand the notation? You understand conceptually what the sequence, what the planner is doing here in the growth model? Okay, what I want to do now is take a step back and analyze the sequence problem and the functional equation in a generic or a canonical form. All right, so not talk about the optimal growth model specifically. The objective for our class today, and I'm not sure I'll be able to finish all of it, is we want to establish the set of conditions that are necessary for solutions to the sequence problem to be equivalent to solutions to the functional equation, or the Bellman equation, in a stochastic environment. And then we can derive or establish a set of conditions that fully characterize the solution to these sequence problems with uncertainty in them, so that we can apply those conditions to the optimal stochastic growth model next week. Okay, so let me write what the sequence problem looks like in kind of generic form. I'm going to define x tilde of z superscript t to be this plan that specifies the value of xt plus 1, which has to be an element of k-dimensional Euclidean space, for a particular history of shocks up through period t. So x tilde squared brackets z of t, or z superscript t, is a specific value for xt plus 1 contingent on a certain realization of the shocks up through period t. That's going to be our control vector in this problem, right? So what the sequence problem looks like then is that the value function v star, which depends on the initial state and the initial shock, is equal to the max over these infinite sequence of state contingent plans for x of the expected value conditional on date 0 information, the sum from t is equal to 0 to infinity of beta to the t u of x tilde z t minus 1, in other words, xt. That's the state. The control is x tilde z to the t. That's xt plus 1. And then also the current shock. Subject to the control being an element of the constraint set, G, which depends on xt and zt. Okay? Again, what is the planner doing in the sequence problem? She is choosing an infinite sequence of these state contingent plans, right, where x tilde assigns a specific value for xt plus 1, conditional or contingent on one of the possible histories of the z's over time. Okay? So unlike the model that has no uncertainty, the planner here is choosing a sequence of contingency plans over time. In a model where there's no uncertainty, there's just a single sequence of values that are being chosen over time. Okay, so it's quite different here. At each point in time, you have to think about all the different possible histories of the z's that could lead up to that particular state of the world. V star is again the value function here it's the value of pursuing a sequence of contingency plans that maximizes the right-hand side. We've talked about the conditional expectations operator. We've talked about the constraint correspondence. What else? Just like the model without any uncertainty to it, the solution to the sequence problem, because we're trying to characterize an infinite number of state contingent plans, is very difficult to work with analytically. It's difficult to characterize the solution to that. Instead of trying to solve for all of those, what do we want to do? We want to transform the problem into a functional equation where we can solve for directly the optimal way that xt zt maps into xt plus 1. That is, solve for the policy function instead of these infinite number of state contingent controls. Okay? The functional equation that suggests itself from the sequence problem takes this form. V of xz is equal to the max of x prime on g of the current return, that is u of x, x prime z, plus the discounted expected value of the continuation return, v of x prime z prime, conditional on what is known about the shock in this period. And that's for all x on big X and all z on big Z. Because time only enters the utility function or the payoff function indirectly through the variables themselves, there's no reason to expect the policy function to be time varying, right? So it's a time invariant policy function that we are maximizing over here. That's what corresponds to x prime. Now, just to be clear, the other objects here, v is again the value function that tells us what the value is of pursuing an optimal policy function in this functional equation, and x prime represents the control as the policy function. So instead of trying to find this infinite sequence of state contingent plans, here we're really just trying to find a single policy function that determines how the control vector is set based on knowledge of what the state variable is, x, and the current value of the shock. Okay. What we want to do today is to try to present some results on the relationship between solutions to SP and solutions to FE to mirror our discussion of this stuff from earlier in the semester when we didn't have any uncertainty. And there's also a few results regarding the concavity of the value function and the monotonicity of the value function and the differentiability of the value function. Some of this is going to be new because now you'll see that the value function depends not just on the state, but also on the shock. And it turns out we're going to need to know something about the monotonicity of the value function, not just with respect to x, but also with respect to z. So there are a few new assumptions here that are going to be important when we're proving certain properties in the optimal growth model. Okay? Now, to develop these points, I'm going to make use of a definition that looks similar to one we talked about earlier. I'm going to define capital phi of xt zt as the set of all feasible sequences of state contingent plans, starting in period t and going to infinity. So it's the set of all of these sequences of state contingent plans such that each state contingent plan, x tilde of z, is feasible. That is, it lies inside of the constraint correspondence. Right, so what capital phi of xt zt is just the entire menu of choices that the planner has when attempting to maximize the sequence problem, okay? All right, so what I want to do now is go through, and I'll try to do this a bit more briskly today because a lot of this mirrors the discussion that we talked about earlier, but I want to go through the set of assumptions that are needed to establish the theorems that give us equivalency between the sequence problem and the functional equation. All right. What is the first assumption? And hopefully this will be a bit of a review, by the way, for your exam. When is your exam again? This week, right? Friday. What's the first assumption? The first assumption basically has two parts, right? And this, I'm not going to write it all down, so I'm going to read a lot of this from the notes, but I'll jot down a few things to help clarify points. The correspondence g of x z is non-empty valued for all x on big X and all z on big Z. Moreover, for any initial values of the state, that is x and z together, and for any feasible sequence of contingency plans over time that the planner can select, the objective function has to exist, meaning that the limit as n goes to infinity of the expected value of the sum from t is equal to 0 to n of beta to the t, u of x tilde zt minus 1, x tilde zt, z subscript t, conditional on z0, has to be finite and exist. So there's two parts here to this assumption, if you'll recall this. It says that the planner has to have some menu of options to select from in trying to maximize the sequence problem, right? G cannot be an empty set. Therefore, the sequence of feasible plans can't be the null set, right? And furthermore, in order to be a well-posed maximization problem, the object that you're trying to maximize, the expected discounted lifetime utility function, has to actually exist in order to maximize over it. Okay. If assumption is 1 is satisfied, then that immediately implies theorem 1, which I believe we called equivalence of values, right? And what did that say? For any x on big X and any z on big Z, V star that is a solution to the sequence problem, or that I should say attains the maximum value of the sequence problem, also attains the maximum value of the functional equation. Moreover, any solution V to the Bellman equation also attains the maximum value of the sequence problem, so that V star of xz is equal to V of xz for any x and for any z. So as long as assumption 1 holds, that is, there's a non-empty set for the planner to choose from, and the objective function exists, then we know that the maximum value of the sequence problem corresponds to the maximum value of the functional equation. They have to be equal. Assumption 1 is also enough to give us theorem 2, which I think was called the principle of optimality. This is a super important one, perhaps the most important one in the set of dynamic programming theorems. If assumption 1 holds, then for any initial values of x and z, let's assume that x bar star is some feasible sequence of state contingent plans starting at date 0, okay, that attains the maximum value of the sequence problem. That is V star of x0, z0. Then we can write the sequence problem in 2 pieces. It's not just the infinite sum of period payoffs, but rather we can write the optimal value of the sequence problem as the following. The optimal value of the current return plus the discounted expected value of the continuation return. Conditional on what is known in period t. Everybody see that? So If we've identified a sequence of contingency plans that achieves the maximum value of the sequence problem, that is V star, then V star can be written as the maximized value, the optimal value of the current return, plus the discounted conditional expectation of the continuation return. Okay. Now, why is that useful? Well, in view of the fact that Theorem 1 gives us that the optimal value of the sequence problem is equal to the optimal value of the functional equation, then if the principle of optimality says that we can break up the sequence problem like this, then that means V is equal to U plus beta expected V conditional on Z, right? We just substitute V's for V star, or V's for V stars. And this is exactly the functional equation. So if we've identified any feasible sequence of plans that achieves the maximum value of the sequence problem, it also achieves the maximum value of the functional equation. What's the obvious implication then? We can go from solutions to the sequence problem to solutions to the functional equation without running the risk of excluding any possible solutions to the model. Remember, what's the objective here? We're given a sequence problem. We would like to solve a different problem. That's only going to be useful if solutions to that different problem correspond to solutions to the original problem. What the principle of optimality implies is that we can find solutions to the functional equation, and we're not going to risk excluding possible solutions to the sequence problem. So the two problems are going to give us equivalent solutions. Okay? Let me go back to the assumptions. What was assumption 2 in the deterministic version of the dynamic programming problem? It had to do with the compactedness of the state space, right? Assumption 2 is going to then require that big X, that's the space that X lies on, is a compact subset of Rk, which means that it lives on a closed and bounded interval if we're talking about one-dimensional Euclidean space, right? That's I believe, the Hein-Borel theorem. What else? Z, remember, big Z is also compact by construction. We've given Z a discrete topology, right? So it's going to be compact by assumption. That means that X times Z will be a compact set. If X is compact and Z is compact, then their product is going to be compact. If we define, let's say, X bar G as the set of all triples X prime Z that live on X times big Z, such that X prime is feasible, then we know that the domain of our dynamic programming problem is going to be compact. Okay? Why is that important? You guys remember? Why was it important for the state space in our dynamic programming model to be compact? What did that give us?
Because a unique value function exists.
It's important to determine that a unique value function exists, and also important to establish it's important to establish that the lifetime objective function exists in the first place, right? Remember, if the state space is compact and the utility function to boy is continuous, then that means the utility function is bounded, right? And if the utility function is bounded, that means that the infinite sum of discounted lifetime utilities is also going to be some bounded number. It's going to be less than infinity. So this was really important in order to establish that the overall objective function exists in the first place, which then was helpful in establishing the existence and uniqueness of the value function itself. All of that still holds here. X is compact, Z is compact by assumption. Therefore, the state of X prime Z is also going to be compact. This was enough to establish Theorem 3, I believe, which we called existence of solutions. Suppose that the first two assumptions hold, then there exists a unique, just as Tavoy said, a unique value function V that maps elements of X product Z into the reals that satisfies the Bellman equation or the functional equation. The function V is continuous and bounded in X for any possible realization of the shock. Moreover, an optimal plan has to exist for any possible initial values of X and Z. Two major results in that theorem. One is the uniqueness of the value function and therefore the Bellman equation in these stochastic dynamic programming problems. If we combine this with Theorem 1, this then says that the value of pursuing an optimal plan in a sequence problem is also unique. If V is equal to V star by equivalence of values, then the uniqueness of the Bellman equation implies the uniqueness of the value function to the sequence problem as well. However, we haven't established yet necessarily that there exists a unique optimal plan that achieves the value function. It may still be the case that there are multiple plans, multiple sequences of state contingent plans that achieve the maximum value of the dynamic programming problem. How do we rule out that as a possibility? How can we ensure that there's only a unique policy function that achieves the maximum of the Bellman equation? What additional assumption is needed to be made?
Assumption 3.
Which was?
That the utility function is concave.
Right, the value function has to be strictly concave,
And then the
right?
policy function would be convex.
That's so. If the value function, in order for the value function to be concave, the utility function has to be concave, and the constraint set has to be convex, right? But it's the concavity of the value function that ensures the uniqueness of the policy function. That was true in the deterministic world. That's also going to be true here in the stochastic world. Assumption 3 says that the period payoff function, or the utility function that we've called it, is going to be concave. You guys remember what that means? If you take any alpha between 0 and 1, and you take any x that's not equal to y, let's say, where x prime is in g of x z, and y prime is in g of y z, then the utility function evaluated at the linear combination of these 2 points, x and y, so that is alpha x plus 1 minus alpha y, comma, alpha x prime plus 1 minus alpha y prime, comma, z has to be strictly greater than the linear combination of the utility functions evaluated at the 2 points distinctly. That is alpha u of x, x prime z, plus 1 minus alpha u of y prime, z. I'm not going to prove that. We did it in the deterministic world. It's the same proof here, okay? And this must be true for any possible value of z. So the utility, the payoff function needs to be concave. And Richard, what else did you say? No, there was one other condition in assumption 3.
That the constraints convex.
G of x, z must be convex. Meaning that, again, if you take any alpha between 0 and 1, and you take any two distinct points, x and y, then the convex combination of x prime and y prime has to live inside of the constraint set determined by the convex combination of x and y. For all possible values of z. If we are willing to make that basic assumption, which is very standard in economic problems, that is the concavity of the utility function and the convexity of the constraint set, then that's enough to give us Theorem 4, which we call the concavity of the value function, which says that the unique value function that we identified in the previous theorem, Theorem 3, is strictly concave in x for any possible z. So v of xz is concave in x for all z on big Z. Be careful about that. It's strictly concave in x, not in z. And
Is it
what-
necessary to show that
Sorry?
Is it necessary to show that it's concave in z? Is that,
We don't need that.
oh,
We're not going to need that. We will need for it to be monotonic in z, but we don't need to show that it's concave in z. The other portion of Theorem 4, which I believe was actually a corollary in the earlier discussion of the model with no uncertainty, was that the concavity of the value function then directly implies that the optimal plan is unique, right? That is, this sequence of state contingent plans, let's call it x tilde z of t, that achieves the maximum value of the sequence problem, and therefore also achieves the maximum value of the functional equation, can be expressed as a time invariant function of the current state and the current realization of the shock, right? That is, the optimal value of xt plus 1 is equal to pi of xt zt, where pi is a continuous function that maps elements of big X times z into big X. Right? So we really don't need, if you think about it, we really don't need to make a whole lot of stringent assumptions on these problems to generate a unique policy function, right? We've got to have something that the planner can choose. G has to be non-empty. The lifetime objective function has to exist. Okay. The state set has to be compact, and the utility function has to be continuous and concave, and the constraint set has to be convex. Given those very standard assumptions about extremum problems, we can establish the existence and uniqueness of not only the value function v, but also of the policy function pi. It is not always the case in real world applications that the payoff function is going to necessarily be continuously differentiable. But in all of the applications that we're going to deal with in order to illustrate the power of these theorems, we're going to assume that the payoff function is continuously differentiable. That way we can take advantage of differential calculus to characterize the solution to the problems. We don't have to resort to strictly numerical techniques. So the optimization problems, or the solutions to the optimization problems, can be characterized with first order necessary conditions. Okay. If we're willing to make that assumption about the differentiability of the payoff function, that leads directly to Theorem 5. No, I have skipped one, haven't I? Yes. I'm going to go backwards here. I'm going to skip one and come back, okay? That's actually Theorem 6 in my list of notes. Okay, so no one's confused, right? I'm skipping one of the theorems. Theorem 6 is the differentiability of the value function. Okay, the utility function is differentiable. The value function is going to be differentiable. And more importantly, when we take the derivative of the value function with respect to the state, we can evaluate it by exploiting the fill in the blank. Envelope condition, right? Remember, the gradient of the value function with respect to the first k arguments, that is the derivative of the value function with respect to the state, would be equal to the derivative of the payoff function with respect to the first k arguments, that is with respect to the state, holding constant the optimal value of the control, x prime star, which is given by pi of xz. Right, this is the envelope condition. You guys understand intuitively what the envelope condition is? Yeah. So I think I saw a,
We did like a, yeah, I think it was the week before last week in micro.
Yeah.
We did like a 45 minutes of envelope condition deriving, proving the extended demand, proving the lambda,
okay.
and so on.
But intuitively, I want you to understand what it is, right? I mean, the value function is the indirect lifetime utility function, correct? Remember what indirect utility is. It's the value of utility evaluated at the optimal consumption bundle, okay? I saw someone on Twitter the other day give a nice analogy or nice analogy of what the envelope condition says. Imagine that Richard, imagine that you have to drive to school every day from your apartment. Okay, you live, let's say, 5 miles away. And there are literally dozens of different ways that you could get to school or work, right? A bunch of different directions and roads that you could take. Your choice is to try to find the optimal path to school. That's your dynamic programming problem. And let's say you select a path that has you go up McFarland and you turn on to University and then you go over to Campus Drive. Okay, that's the optimal. Given the amount of traffic that you have and given the distance and everything, you've determined what the optimal path is. Okay. What the envelope condition tells us is, how does your choice, how does the time it takes essentially for you to get from your apartment to work or to school change if some exogenous factor changed, like they put in a new red light on your existing route, or they got rid of one of the lanes on your existing route, right? So if there's some exogenous change on on the route that you optimally take to school every day, how does that affect the total travel time? That's one, I think that's one useful way to think about the envelope condition, right? It's, you've already determined what your optimal decision is. And what you want to think about is, how does a marginal change to some exogenous factor, like an additional red light or an additional lane or an additional railroad crossing, affect the value of your dynamic program, which would be the time it takes for you to get to school, right? That's what you've tried to minimize, right? And you've got all these different possible routes that you can take. That's kind of what the envelope condition is, right? And the beauty of it is that you do not have to take derivatives through the policy function. You can ignore the policy function in taking the derivative of the Bellman equation, right? And the reason why is that if you actually physically do the chain rule and carry through that differentiation, all those terms cancel out due to the first order conditions of the maximization problem. You're going to find that you got these terms that will be equal to 0. Okay, that's what the envelope condition is. Now, without trying to confuse you even more, let me go back, because I think I forgot assumption 4. So we talked about the differentiability of the utility function, but what about the monotonicity of the utility function? Assumption 4 says that for each x prime in x and each z in big Z, that u of x, x prime, z is strictly increasing in x. So if you increase the value of the state vector, you increase the current payoff function for any feasible x prime and any choice of z. Moreover, the constraint correspondence, G, is monotone. You guys remember what that means? What does it mean for the constraint set to be monotone? It's not a function, so it's not increasing in the traditional sense of the word, but it is a monotone set. What does that imply?
So like if we increase the set of values that x can take, then the control can take additional values based on.
That's right. So let's say you've got an x that is less than or equal to some y. Then this implies that g of x z is fully contained in g of y z for all possible z, correct? So the set of g's determined by y is bigger than the set of g, it contains the set of g's determined by x, as long as y is bigger than x. That's what it means for the constraint set to be monotone. Now, if we are willing to make that assumption, then we can establish Theorem 5. So again, I know I skipped one here. I'm going back to Theorem 5, which was the monotonicity of the value function. And I'm going to call it part 1, because there's a second part to this that has to do with monotonicity with respect to z rather than x. Okay. Suppose that all of these assumptions we've talked about hold, then the unique value function established earlier, that is a solution to the Bellman equation, is going to be strictly increasing in x for all z in big Z. And of course, if v is differentiable, then what that just means is that the gradient with respect to v, with respect to the first k arguments, is strictly positive for all z. Okay. All right. let me talk about something that is a little bit new now. So we have to have some, it turns out that we're going to need to be able to make some assumptions about the behavior of Z and its relationship to the utility function and the constraint set. This is assumption 6. It has 3 parts to it. So this is what's different than our earlier discussion in the semester. Number 1, G is monotone in Z. So not only is the constraint set monotonic in X, it has to be monotonic in the shock itself, Z. Meaning that if you have some Z that's less than or equal to, let's say, a Z hat, this implies then that G of X Z is fully contained in G of X Z hat for all X in big X. So please remember that. The constraint correspondence in these stochastic dynamic programming problems is going to be monotonic not only with respect to X, but also with respect to the shock Z itself. Part 2. For any X prime Z in X bar of G, so that is any feasible triple X prime G, U of X prime Z is increasing in Z. So not only is the payoff function increasing in the state variable X, it also needs to be increasing in the shock Z itself. If the technology shock increases, think about it, that's going to increase production and increase output, which should also increase consumption and therefore increase utility. So the optimal growth model is going to satisfy this assumption. But in general, the shock in the model, or the vector of shocks in the model, have to increase period utility, not decrease it. Now, of course, that's not totally restrictive, because if you imagine a model that has certain shocks that would tend to dampen utility, you could always define those shocks as the negative of themselves, and they would increase utility, right? But since Z takes on this discrete topology, then the way we write this is that, you know, U of X prime, let's say Zi, that's one of the shocks, is going to be less than U of X prime Zj for all J bigger than I. Remember, we wrote the shocks in ascending order. So if Zj is bigger than Zi, then that means U of Zi is less than U of Zj. We can't take derivatives with respect to Z, obviously, because it's a discrete random variable. If we're dealing with a continuous random variable, like we do in many macroeconomic applications, you could take the derivative. But that would be a general Markov process instead of this first order discrete Markov process that we've talked about in this class. Okay, any questions so far? So G has to be monotone in Z. The payoff function has to be increasing in Z. There's one final assumption here that is really not intuitive, and that is that the Markov chain for Z has to be monotone. So the stochastic process for Z, that is this Markov, first order Markov process, has to be a monotone Markov process. Now, what exactly does that mean? Okay, a random variable exhibits a monotone Markov process if you take any non-decreasing function F, which maps elements of big Z into the reals, if for any non-decreasing function F that maps Z's into the reals, the expected value of F of Z prime conditional on Z is also non-decreasing in Z. That's what it means for a stochastic process to be monotone. If you take some, basically an increasing function, let's call it a production function that depends on the state of technology, right? Think about a production function where Z is just a neutral production productivity shock, right? So higher values of Z increase the amount of output that we produce. That would be an example of a non-decreasing function of Z. Then what this says is that the expected value of next period's production, conditional on today's productivity shock, is going to be higher if we observe a higher productivity shock today. So higher levels of productivity are expected then to generate, or an expected value, higher levels of productivity and therefore output in the future. That's what it means for Z to follow a monotone Markov process. Now that seems like a rather restrictive assumption, and it is strange, but it's going to be useful when we try to prove certain properties of the Brock-Merman model next week, particularly regarding the existence and uniqueness of not the steady state, but of the stationary distribution. Think about it. There's no fixed steady state in a model with random shocks, right? Because even as time approaches infinity, there's a new realization of the shock every period, which is going to cause you to bounce around some steady state in the long run. But there will be, under certain conditions, a ergodic stationary distribution for our endogenous variables in the long run. So instead of converging to a steady state, we hope that our variables converge to a stationary distribution in the long run. In order to establish that, you need this monotone Markov process. Okay. This is enough then to establish Theorem 7, which is the monotonicity of the value function, and I'll call it part 2, which says that if all of these assumptions hold, including this most recent one I've just talked about, then V is strictly increasing in Z. So not only is the value function increasing in a state variable X, it should be also increasing in the shock itself. So V of X Zi is going to be less than V of X Zj for all j bigger than I. Again, if the Z's are written in ascending order, okay? Again, this particular theorem, we're going to call on it when we prove certain useful properties of the stochastic optimal growth model. Okay, I don't really have enough time to quite finish this discussion. Here's what we need to do to finish this. I want to, when we discussed basic dynamic programming in the deterministic world, right? We talked at length about these various assumptions and theorems that establish the equivalency between the sequence problem and the Bellman equation. The purpose of that was not for you guys to prove those theorems, but rather for you to get a kind of a workman's or practitioner's knowledge of how to apply dynamic programming tools in application. That culminated in a particular theorem which says that the solution to these dynamic programming problems are characterized by two conditions: an intertemporal Euler equation, which is derived from the first order condition of the Bellman equation combined with the envelope condition, and a transversality condition. So there are two equations, two conditions that characterize the solution to dynamic programming problems: the intertemporal Euler equation and the transversality condition. There is an equivalent or analog theorem in the stochastic world, which basically says the solution to stochastic dynamic programming problems can be characterized by two conditions: a stochastic intertemporal Euler equation and a transversality condition. I want to talk about those for the first 20 or 30 minutes of class next week, and then we will move on to the Brock-Merman model. Really, the only difference here in application is that the stochastic Euler equations end up not only having to hold for all time t, like in the deterministic world, they also have to hold for every possible state of nature. That is, every possible realization of the shocks. So in a stochastic world, the Euler equations hold at all dates and all states. In the deterministic world, it only has to hold in all dates because there's only one state of the world, right? The transversality condition, however, even in the stochastic world, there's only one of them because it is evaluated by taking the conditional expectation at date 0. So both of the conditions end up looking a little bit different than what we had in the model with no uncertainty, but there's a lot of similarities. So I want to set up the basic problem, derive the first order condition, the envelope condition, and use it to write down the stochastic Euler equations that must hold at all dates and states, pair that with the transversality condition, and then once you guys have kind of mastered how to derive those, you should be able then to set up and characterize the solution to these stochastic control problems, which are the basic tools we'll need to analyze the Brock-Merman model, and are the basic tools you will need to analyze any of the business cycle model or asset pricing models that you talk about next semester. We'll do that, and then we'll move directly into the Brock-Merman model. So I'm just a little bit behind schedule right now, okay?